Guys, welcome to my YouTube channel. Today we have talked about the molar mass concept previously, and there was three formulas that I told you that is necessary for any chemist to know about, and I'm just going to write them down real quick. The molar mass is the number of grams per mole. You could solve it for n, that n would be the mass divided by the molar mass, or you could solve it for mass as well. The mass would be number of moles times the molar mass. Okay, so these three formats of the molar formula we've talked about previously, but there was a question that we didn't talk about, and that was about how to obtain the molar mass of a compound, of a given compound. Let me go on and talk about the molecules, some molecules. We'll talk about their molar masses, and let's talk from the simplest one here, the CH4 molecule. Everybody could see that there is a carbon and there are 4 hydrogens, and as we go to our periodic table, we could see that the mass for carbon is this number that is right down here. So it's going to be 12.0 whatever. I just take the decimal, first decimal, and round out to that. So this is 12. And for hydrogen, you could see it's already 1.007. That it actually 1. So if we took one of these hydrogens to actually each of them weigh 1 gram, and the carbon weigh 12 each mole actually, and the mole being that big huge number that is 6 times 10 to the 23. That's the number of particles, like that many of this CH4 molecules would make up a mole of CH4. So the molar mass for CH4 would then be 12 because of the carbon and 4 because of the hydrogen, 16 gram per mole. That for an oxygen molecule which has 2 oxygens in it would be, again, if you look at the periodic table, you could find oxygen here that is 15.999, and if I round it up to 1 decimal place, it would be 16 times 2, it would be 32 gram per mole. That of a nitrogen, 2 nitrogen molecules, each weighing 14, if you refer to the periodic table one more time. So the molar mass for N2 would be 28, 14 times 2 gram per mole. And that of ammonia, NH3, would also be 1 nitrogen, which is 14, and each hydrogen was actually that 1. So NH3 would be 14 plus the 3 would be 17 gram per mole. And that of phosphorus that you could see here, the P4 molecule, would be 4 times the 31.0. That is the molar mass of P4. That would be 124 gram per mole. Okay, 4 times 31. So this is how we compute the molar masses of different substances. And if you look, we could have actually any molecule and go on and count the number of atoms, look up the weight of each of those atoms in the periodic table, sum them up, and that would be the molar mass. So that's pretty simple. Okay, so this is how we go about it. Now I'm going to go on to use actually these formulas in real chemical reactions. Okay, we will talk about balancing chemical reactions later on, but for now I just want to talk about specific examples. We will move on little by little from the yields to percent yields to sort of mole concept problems, and then finally we will talk about limiting reactant case that we will also talk about it. I would talk about general strategies first, and then we will move on to specific problems. So let's talk about the general strategy here. If you have A plus B giving us C as a chemical reaction. Let's say 2A plus 1B gives you 3C. Then what you would do is that there is a molar coefficient for that specific reactions, and there is a molar mass for each type of those compounds. You would need the molar masses for each component, and if you have any of these grams in a reaction provided, you could compute any other substance in that reaction. Only and only if you have one of the reactants. Okay, so if the reactants you're being given two of the reactants, then the problem is not going to be as simple. But we will talk about it. That's the case of the limiting reactant. But if somebody provided you with one of the reactant or a reactant and a product, then you could talk about any other possible compound that is in the reaction and talk about how much of that material. Like if somebody gave me 10 grams of B, I could predict how many grams of C can be produced, and I could also predict how many grams of A is going to be needed for that reaction based on the information and the molar masses. Okay, and how do I do that? Let's go to the specific examples, talking about those cases. That is the easiest use of mole concept problems. Let's say we have 12.82 grams of actually, let's go to this very simple problem first of all, and that is a problem of this reaction, C2H5OH plus O2 giving you CO2 and H2O. Okay, so there you could see the coefficients, and each of those reactants, each of those compounds that has been separated from the other with a plus, you could have a molar mass for that, for those. The problem tells you that 225 grams of your fuel, which is the ethanol, is being burned. This is a combustion reaction, by the way. We will talk about different classifications and also how to balance reactions later on, but for now we just use the reaction and use the mole concept to actually address the problems. So if you have this much mole of your fuel being burned in oxygen, the problem is how much CO2 and how much H2O is going to be produced. Okay, so first I need the molar masses of every one of those. Okay, so just to go back here, 2 carbons, which make 24, 6 hydrogen, which makes 26, and then 1 oxygen, that is 16, gives you a 46. Let's just check. 24 plus 6 plus 16 . That is 46, and then 32 for oxygen, because 16 times 2, and carbon 12, 2 oxygens for CO2, that would make 44, and oxygen, we didn't do that, but oxygen is 16 and hydrogen is 1, so 2 plus 16, that's 18 grams per mole. So these are the molar masses. And based on the formula that we have on the top, if we have the grams of any substance, we could compute the moles. Okay, so the strategy is to start from this, and the problem is asking for this one, how much CO2 and how much H2O is being produced. So first we go, let me take another color for this one. Let's take orange. Let's talk about starting with my ethanol, my fuel. I start by converting the grams of it to the moles, and then I have the molar ratio based on the coefficients that I have. Okay, and then I will came up with the idea of how much of CO2 would be produced. Okay, so that's the strategy. Now let me just write down what we have. Based on this formula on the top, the grams is 225 divided by the molar mass, which is 46, then the molar ratio, and then times, this would provide me the number of moles. So that's this, using this formula, because I'm predicting the grams of CO2, and this whole thing until here would give you the moles of your CO2. Okay, I'll talk about the molar ratio, how it provides you with the moles of CO2, but let's just assume that this whole thing is moles of CO2, and then it should be times the molar mass of it, which is 44, to give you the gram for CO2. Okay, now how do I go? This thing will give you the number of moles for your ethanol, for this one. Okay, but how do I move to the moles of CO2? Like, how do I go from here to here? From the moles of my ethanol to the moles of my CO2. Okay, that's the trick here. The one that you start with is the moles of your fuel, your starting material, and that's only one. The coefficient is 1 here. If we don't write it down, that means it's 1. And 1 mole of it would produce 2 moles of CO2, so you put 2 at the top. So number of moles of your fuel, which is the mass divided by the molar mass, times the molar ratio. On the denominator, you wrote down the things that you started with, so you want to get rid of. Okay, so moles of the fuel, the ethanol, would cancel out, and the moles of the thing that you desire would actually show up on the top. That would produce the moles, this N, for CO2, and when you multiply it by 44, it would get the gram of CO2. That's the whole format for any problem that is not a limiting reactant. Okay, again, a limiting reactant is posed when you have 2 of the reactants. Here we're just being given this one reactant, and we could provide this or this. That we will do real quick. So here, if we do that, we will find out that it would be 430 grams of CO2. You could do it this way, this divided by this, then times 2, then times this, or you could do it the whole way and then divide it by the whole numbers. So this times 2 times 44 divided by 46. Anyway, you're anywhere that is easier for you, that would be good enough. Let's now do the same thing, and here on the second part, I'm going to actually be interested in H2O instead of CO2. What then I should put in this one, in this part? It should be H2O. Okay, and my molar ratio also should put the moles of H2O here, which is 3. Okay, again, my grams is 225 divided by 46, and I do actually put the molar ratio times, now this will give you moles of my water, because I have done the molar ratio. Molar ratio thing just allows you to jump from one compound to any other compound in the reaction. So that's 18 here, and if I do that, I would find out that it would be 264.1 gram of H2O. Okay, so that's this, and with this I want to move on to yet another example. See if I could manage to do it in real time. Here, let me just move on to yet another example. Now, what if the problem is not going from a reactant to a product, but going backward? It would be very the same procedures, only the direction that you move would be different. Now, let's say this is our reaction. 2KClO3 gives us 2KCl plus 3O2. Again, you have to go on and write down the molar masses. The molar mass for KClO3, again, this is just the summation that we did for this set of molecules at the very beginning of this video. From now on, because I want to run fast, I don't redo the molar masses in front of you. You could just sum them up, sum the mass of potassium from the periodic table and a chlorine and 3 oxygens, and you would get these numbers that I'm writing down. These are called the molar masses: 122.6, 74.6, and 32 grams each mole. Okay, and if the problem tells you that we have a sample, it's an impure sample and it weighs this much gram, that's the mass of your impure sample, and it produces 3.73 grams of oxygen. what is the percent of KClO3? When it says it's a sample of KClO3 and it's impure, you know not all the 12.82 grams of this sample is this. So you can't just divide it by the molar mass or take it as 100% pure, okay? So what you want to find out is that if you are given this reactant, only one component of the reaction, how much of this you're going to get. This is the direction. Now it's reverse, going from that to that, okay? And I could say I start with my O2 there, and I want to end up getting my ClO3, okay? And my molar ratio should also work backward. If I go from this, the one that I start with should go on the bottom, and the one that I end up having should go on the top. I have this much gram of oxygen being produced. If there is no comments, it means this thing is pure oxygen. Only when somebody tells you an impure sample, you want to be careful with this weight, because this is not KClO3, or not all of it is KClO3. So to find the purity percent for this sample, first we need to find how much of this whole thing is KClO3. That's why I decided to move on from O2 to KClO3. So there is 3.73 grams of my oxygen. That's the molar mass divided by 32. I want to get rid of oxygen because I'm moving from oxygen, so 3 goes down, and I want to end up having KClO3. Now this whole thing will give me the number of moles for my KClO3, and if I multiply it by 122.6, that would give me the grams for my KClO3, and that would be gram of KClO3, and that's 8.61, and if you do 8.61 divided by 12.82, this would give you how pure your sample is, and that times 100 will be 67.2%. That's the purity of the sample, and that is how we do it. So that is yet another problem, and the only trick is that be careful about an impure sample. You can't take this whole thing as KClO3. Only 8.61 gram of it is KClO3. Others is junk, and that's what make it impure, and you could calculate the percent by that. Let's move on to yet another problem. Okay, now another problem, and I want to wrap up most probably. Hopefully this video doesn't took that long, but I want to wrap up with this problem. FeS2 plus 11O2 giving you 2Fe2O3 and SO2, 8SO2. This should be 4FeS2. Okay, the molar masses are going to be, again, I have already computed the molar masses, and you should know that you will need a periodic table. Fe is 55.8, as you can see, and if you take 1 Fe and 2 sulfurs, add them up together, sulfur is 32.1. I just take the first decimal place, that would be enough, okay? And then you could work out all these molar masses. These are not something that are something strange or coming from a weird place, okay? They're just the molar masses that we showed at the very beginning of this. So this is this. For O2 is 32, for Fe2O3 that's 159.7 and 64.1. There it is. Now we have the molar masses, and the problem tells us if we have 38.3 grams of 38.8 grams, my bad, of FeS2, and it produces 40 grams of SO2. 40 grams of this is produced. What is the percent yield? Okay, so the first problem is that if you have something like this, like a given reactant and a given product, you should know that there is another amount of this that can be produced, and that's the maximum amount. Okay, we call it the theoretical yield, and with this problem I want to introduce two other concepts. For the first two previous problems, that's the maximum amount that we're talking about. We just take the benefit of the moles and the grams, and we use the maximum amount. That's the theoretical yield, whether we're going from this side to this side or the other side. Okay, but we could have in real situation that you put this much of your reactant, and instead of getting maximum amount, you will getting something less than that. Okay, that means you have a yield. Okay, a yield of a percent yield for the reaction. It means not 100% of this is going to be converted to SO2. Okay, now if you have that, if the product is being given to you and you're being asked for a percent yield, you should know that this is not your maximum possible how to say product. This is called the actual yield. Okay, or what you took as reality. If you take this actual yield and you compute the maximum amount, just like we did for the two previous problems, you could then divide the actual yield, this one, with the maximum amount that I'm going to compute, and then you could actually get the percent yield. Okay, so let's first do the actual amount, and then finally we're going to address the problem. The problem simply asks what's the percent yield, and to get that we should have the theoretical yield, and the relationship between those two is actual yield divided by the theoretical yield is your percent yield. So that's the formula. Okay, so this formula always holds. Theoretical yield is the number that even if you don't have anything, just have the mole concept, just like we did for the previous problem, you can always compute or calculate theoretical yield. Okay, and for the percent yield, it's needed. First you have to have this, then you could divide 40 by that number to get the percent yield. Okay, let's go on from using this to SO2. Now we have 38.8 gram of FeS2 divided by 120.05. I'm going to move on from this to this, so 4 would go on the denominator, 8 would show up on the top, times the molar mass, which is 64.1, and if I do that, I will find that that would be 41.4 gram of SO2. This is possible, and this we call the theoretical yield. Okay, so that's TO yield. Okay, now I have the TO yield. I could go on to formula here, and I could say my actual yield, which is 40 divided by 41.4 times 100, will give me my percent yield, that is going to be 96.6%. Okay, so that's your percent yield. That is the final answer for the percent yield. Anytime you have a percent yield, you should compute a theoretical yield in order to be able to actually get the actual yield, or if you provided the actual yield, you also need the theoretical yield that to be able to calculate the percent yield. Okay, so I want to wrap it up here. We will do more examples of this, and when we move to limiting reactant, we will talk about cases where you have two substances and two of them are competing, and what do we do then. Okay,